In this video, let us derive Hamilton's principle from D'Alembert's principle. For this, let us choose a system which consists of n number of particles of masses mi, and here I stands for the number of particles, that is 1, 2, 3 to n, and these system of particles are acted upon by external forces Fi. Then, according to D'Alembert's principle, which we have already derived in the previous video, D'Alembert's principle can be stated or written as summed over I Fi minus Pi dot into delta Ri equal to 0. Here, Fi is the force acting on the system, minus Pi dot is the reversed effective force, and delta Ri is the virtual displacement. So, let us bring this delta Ri inside. So, we will get summed over I Fi delta Ri minus Pi dot delta Ri equal to 0. For my convenience, I am taking this Fi into delta Ri to the right hand side. So, I get summed over I Pi dot into delta Ri is equal to summed over I Fi into delta Ri. We all know this Fi into delta Ri is nothing but, that is the force into the virtual displacement is nothing but it is the virtual work delta W done by the external applied forces Fi. Now let us evaluate what is this Pi dot into delta Ri. We all know Pi is the linear momentum. So the momentum Pi is given by Mi into Vi. Vi can be written as Ri dot. So Pi dot is written as Mi Ri double dot into delta Ri. Then this Ri double dot can also can be written as d by dt of Ri dot. So Pi dot into delta Ri is equal to d by dt of Mi Ri dot into delta Ri. Now we need to find out what is this value of Ri dot, d by dt of Ri dot into delta Ri. So for this, what we are doing is we are taking the time derivative for Ri dot into delta Ri. Here Ri dot is a variable, delta Ri is also a variable. So we may make use of a differential formula d of uv equal to udv plus vdu. So by this formula, so Ri dot is your u, dv is d by dt of delta Ri plus v is del Ri and du is dri dot by dt. So this is the second term is our interest. So we keep this in the left hand side and bringing everything to right hand side. We get dri dot by dt into delta Ri is equal to d by dt of Ri dot into delta Ri minus Ri dot d by dt into delta Ri. So let us take this as equation 3 and substitute it in equation 2, that is in place of d by dt of Ri dot into delta Ri. Substituting, we get Pi dot into delta Ri is equal to d by dt of Mi Ri dot into delta Ri minus Mi Ri dot d by dt of delta Ri. So we cannot do, we can't change the first term. In the second term, what we are doing is we are writing Mi Ri dot, and there is a rule where differentials can be exchanged. So by that rule, we are interchanging delta and d by dt. By interchanging, we are taking the delta outside and making dri by dt. So we get d by dt of Mi Ri dot delta Ri minus delta, the second term we are writing it as an delta of half Mi Ri dot square. If you do the differentiation of this half mi ri dot square, you will get the previous term, that is mi ri dot delta dri by dt. So this seems like half mi ri dot square is nothing but it is like half mv square, that is the kinetic energy of the system. So putting this in equation 1, yes, in this equation 1, what we get is d by dt of summed over I mi ri dot delta ri minus delta half mi vi square is equal to the virtual work summed over I fi into delta ri. If in case the forces acting on the system are conservative, by definition we know Fi is equal to minus del V, that is we can write forces as the negative gradient of a scalar potential. So minus del V, that is the directional differentiator, so we can write it as minus I into dou V by dou X plus J into dou V by dou Y plus K into dou V by dou Z. And the virtual work done can be written as summed over I Fi into delta Ri. In place of Fi, we are writing minus summed over I into dou V by dou X plus J into dou V by dou Y plus K into dou V by dou Z. And in place of delta Ri, we are writing I into del X plus J into del Y plus K into del Z. But by vector dot product, we know dot product of a vector, we know I into I is 1, J into J is 1, K into K is 1. So this equation can be simplified as minus summed over I dou V by dou X into delta X plus dou V by dou Y into delta Y plus dou V by dou Z into delta Z, or simply we can write it as minus del V. So we know this half mi vi square is nothing but it is T, the kinetic energy of the system. So we can write this. So we can write this equation 5. This is equation 5 as dt of summed over I mi ri dot minus delta t is equal to minus delta v. So the minus delta t in the left hand side is taken to the right hand side, so it becomes delta t minus delta v. So taking this delta outside, we get t minus v. We know what is t minus v, that is the Lagrangian function. Now let us integrate this equation 7 from time t equal to t1 to time t equal to t2, and we know the condition at the end points the change in delta Ri vanish. So integrating this equation 7, we get summed over I mi Ri dot into delta Ri between the limits t1 to t2. On the other side, that is on the right hand side, we know integral t1 to t2 delta t minus b into dt. We all know this mi Ri dot delta Ri, but at the limits t2 and t1 they vanish, so it is equal to 0. So we are left with only the integral on the right hand side. So it is integral of t1 to t2 delta t minus v into dt is equal to 0. In the next step, we are taking this delta outside and we get delta of integral t1 to t2 into t minus v into dt equal to 0. This equation 9 is called as integral form of Hamilton's principle. So we have arrived at Hamilton principle. Now we are going to replace this t minus v by L, the Lagrangian function. So our equation reduces to integral of t1 to t2, del integral of t1 to t2 L into dt equal to 0. This equation represents Hamilton's principle.